Hello, I'm Diyasin, and my topic is flow graph construction control for analysis. So let's begin. So first of all, introduction. So what is compiler? First, so compiler is a software tool that translates source code written in high-level programming language into machine code or an intermediate representation. And so why program analysis is needed? So program analysis helps the compiler understand the behavior of a program without executing it. So what is the importance of control flow in this? Control flow describes the order in which individual statements, instructions, or function calls are executed in a program. So understanding control flow is a fundamental because it determines which part of the code will run and in what sequence and how many times, directly impacting optimization and performance. So let's move forward. So control flow analysis. The definition of control flow analysis is a static analysis technique used to determine the possible execution path through the program. It examines how control transfers from one statement to another via branches, loops, function call, or any conditional statement. What is the purpose? The primary purpose of CFA is to build a model of all possible paths that program can take during execution. And role in compiler design, the CFA is typically performed during the intermediate code generation and optimization phases of a compiler. So what is the importance of CFA? So optimization by understanding control flow, the compiler can apply aggressive optimization such as loop unrolling, constant propagation, and common subexpression elimination only where they are safe and beneficial. And the dead code detection control flow analysis enables the compiler to identify code that can never be reached during execution, known as dead code. Efficient execution. CFA helps in instruction schedule by revealing the dependency between operations. Now flow graph. So a flow graph is a directed graph representation of a program's control flow. So why it is used, the flow graph provides a compact and visual representation of all execution program in all execution paths in a program. It serves as a foundation for many compiler optimization and analysis, including data flow analysis, loop detection, and region definition analysis. Overview of representation. So in a flow graph, each node is a basic block containing a linear sequence of instructions. Now let's see what are the components of flow graph. So first one is nodes, edges, and entry and exit blocks. So each node in a flow graph represents a basic block, a maximum sequence of consecutive instructions with a single entry point and a single exit point. And edges, so this is control flow. So edges represent the possible path of execution within basic blocks. An entry and exit block. So every flow graph has an distinguished entry block that contains the first instruction of the program. So what is a basic block? So a basic block is a sequence of consecutive instructions in which control enters at the beginning and level leaves at the end without any possibility of branching or halting inside the block except at the final instruction. Importance: basic block simplifies program analysis by grouping instructions into individual units. Since there are no branches within a block, so many analysts only need to consider the entry and exit point of each block rather than every individual instruction. So now let's see what are the leaders in basic blocks. So leaders is nothing but a first instruction of a basic block. So identifying leader is a crucial first step. So let's see what are the rules for identifying the leaders. The first rule is first instruction. The first instruction of the program is always the leader. This is because the program execution always begins at the first instruction, making it the natural starting point of the first basic block. And second rule, target the jump. So any instruction that is the target of a condition or an unconditional jump is a leader. Then third rule, instruction after jump. So any instruction that immediately follows a conditional jump, unconditional jump, or return instruction is a leader. These are the three rules for identifying the leaders. So now let's see one example. So with three address code. So here as you can see a is equal to 5 and if a is greater than 0 so go to L1 and a is equal to a minus 1 or else you have to go to L2. So L1 is a is equal to a plus 1 and L2 just print it. So So this simple program will be used to demonstrate the complete process of reader identification, basic block formation, and flow graph conception step by step. First, let's see reader identification. So identification of reader. So reader instruction 1. This is the first instruction of the program by rule 1. The first instruction is always a reader. So E is equal to 5 is a reader. So instruction 2, this is not reader by itself, but it contains the conditional jump. So the target of this jump is L1, which becomes a reader by rule 2. And third, instruction 3, A is equal to A minus 1. The instruction follows a conditional jump in instruction 2. So by rule 3, any instruction immediately following a conditional jump is also reader. Then fourth reader, instruction 5, L1 is A is equal to A plus 1. This is labeled L1 and is target of the conditional jump in instruction 2. So by rule 2, it is also labeled. Then L2 print 8. So this is labeled L2 and is the target of the unconditional jump in instruction 4. So by rule 2, it is also a leader. Now let's see formation of basic blocks. So first one is block 1 contains only instruction A is equal to 5. It ends here because instruction 2 is a conditional jump. So second block contains only instruction 2. This conditional jump is the last instruction of this block because it can transfer control to either the next instruction or to L1. Then third, 3 and 4 contains instruction 3 and 4. Instruction 3 is the leader and instruction 4 is an unconditional jump that terminates the block. Then fifth one contains only instruction 5. It is a single instruction block because the next instruction is a leader. Now block 6 so contains only instruction 6. This is the final block of the program and each basic block contains a leader and all subsequent instructions up to but not including the next leader. The block ends when we encounter another leader or jump return instruction. Now let's see flow graph conception steps. So first of all, we have to identify leaders, then form basic blocks, then create nodes, then add edges, and then mark entry and exit point. So here is our flow graph. As you can see, this is the entry point V1 is equal to 5. Then we have condition if A is greater than 0, then go to L1, and if it is true, then it will go to here, and if it is false, then it has to go to block number 3. So block number 2 contains a condition, then according to the answer, it will go. So if answer is true, then it will go to block 5, and if answer is wrong, if it is false, then it will go to block number 3. So let's see first of all block number 3. If it is false, then it will go to block number 3. So A is equal to A minus 1. Then it will go to block number 4, go to L2, and here just print it. And if it is true, then we have to directly go to block 5, then we have to directly go to block 6. So block 1 is equal to 5. Like here you can see, block 2 contains A this instruction, block 3 contains this instruction, block 4 this, and block 5 and 6 is this. And this is sequential flow, conditional loop, and red color means false, blue color means unconditional jump. So now let's see application, advantages and limitations. So first of all, application. So flow graphs are used in the data flow analysis, loop detection and optimization, register allocation, and code scheduling, reordering instruction within basic graphs. This is the application. Now let's see advantages. So flow graphs provide a compact representation of all execution paths, making complex programs easier to analyze. They enable efficient implementation of global optimization that span multiple basic blocks. Now let's see limitations. So limitations flow graph represents static control flow and cannot capture dynamic behavior such as function pointer, Gaussian method calls, or exceptions resolved at runtime. For programs with heavy use of indirect terms, the flow graph may be incomplete. So constructing accurate flow graphs for highly optimized or obfuscated code could be challenging.